we are honored to be sharing the room today with some sister projects of Photo2Fuel, NEFERTITI and PHOTOsynthesis Project. And here today we have first David Gonzalez from LEITAT in representation of the NEFERTITI Project, who is going to talk a little bit more about the an overview of the project, which is about innovative photocatalysts integrated in flow photoreactor systems for direct CO₂ and H₂O water conversion into solar fuels. So just to introduce a little bit David's profile and background, he holds a PhD degree in organic chemistry since July 2009, course at the Universitat Autónoma de Barcelona. He also worked as analyst of complex mixtures of organic compounds, mainly fragrances and flavors company. After that, he conducted a postdoctoral research focused in the synthesis of nanocatalysts, basically organometallic nanoparticles for hydrogenation of aromatics and Fischer-Tropsch reaction. And since August 2012, he works at LEITAT Technology Centre in Spain, where now he is coordinating the Sustainable Advanced Chemistry area, where he has participated in the development and elaboration of several European projects like NEFERTITI, and his work is mainly centered in reactivity, polymer science, microencapsulation, and characterization techniques. Welcome, David. Thank you very much for coming today here to Seville. Yes, the floor is for your presentation. Thank you.
Thank you, Alejandro. It's an honor to be here. Thank you for the invitation. And as I was talking before in the coffee break with Alejandro, it's really nice to have these opportunities of very similar projects to be presented and have this opportunity of collaboration. And you will see that the central idea of the project it's pretty similar to what is been spread to the moment. I'm David Gonzalez. I work in LEITAT. It's a technological center close to Barcelona, in Terrassa. And we more or less do this interaction between research centers and the industry. So Carl has explained a little bit about the project before, the more industrial part of the project. I will focus more on the general overview of the project and the previous work done at the moment. Okay. Well, the introduction is pretty similar as it's been done before by Aldo and other participants. I'm more focused, we talk all about the same. I'm more focused on the CO₂ concentration in the atmosphere at the moment. This data was 3 days ago. Now we are 425 ppm. The scientific community considers 400 ppm the barrier that means it's impossible to control the temperature under 1.5 degrees, that it was our goal as a society. So, as it's been said, we really have a problem with this, and it's compulsory that we work in this field that I think here we all have the same goals. Okay. If we talk about the different types of renewable fuels that has been explained before, the NEFERTITI project is more focused in the synthetic fuels, and why are working with this? Because of this CO₂ concentration, and because one of the objectives of the NEFERTITI project is to obtain ethanol. Ethanol, it's also possible to be obtained as a biofuel, okay? But during the last years, the European Commission has been doubting if considering biofuels a sustainable fuel or not, okay? Why? Because even they can come from residues, they usually come from crops. So this crop for making fuels is not longer considered sustainable. Well, now the policies are changing again, but that's it. So another point of the NEFERTITI project is that this, as Carl has explained before, Celal has explained before, we are in a two-step project. First, we go from CO₂ to syngas, and then with the syngas we do these Fischer-Tropsch. But this hydrogen necessary for the Fischer-Tropsch is coming at the same time by water splitting together with the CO2 reduction to CO. Okay. This is done photocatalytically, as also has been explained before. Advantages: it's energy savings, it's more simple to proceed, and it needs less infrastructure than other type of processes. But it has a lot of challenges. Now the efficiency, we know it's pretty low. The material stability on the catalyst usually degrade faster than other type of catalysis, more thermal-driven catalysis, and the scalability of the process is more complicated at the moment than the electrolysis, for example. Like I think Aldo explained it just before. The electrolysis is at a higher TRL at the moment than photocatalysis, and that's why scalability is more complicated. If we focus on the NEFERTITI project, as I said, our main goal is directly from CO2 and water, obtain ethanol and other high and higher molecular weight alcohols as propanol, butanol, all this. Okay, this done in a system that connects the two reactors. The first one performing the CO2 and water reduction to syngas, and the second one the syngas to ethanol production. In the middle, we need a separation of the oxygen produced in the first reaction, okay? And at the end, a continuous separation to separate this alcohol from the water produced in the Fischer-Tropsch, okay? One of the most complicated part is in the Fischer-Tropsch reaction of the second reactor is to obtain specifically alcohols, because as you probably know, the Fischer-Tropsch usually produce different molecular weights hydrocarbons. That it's depending on the temperature, the pressure you use. You have a Gaussian, and you go to the hydrocarbons. In this case, we need to stop in the middle, and there are specific catalysts that do this reaction. Okay. The KPIs of the project are very high and very difficult to obtain, but it's very high selectivity of CO2 reduction to CO, and also and high selectivity to CO2 alcohol. Okay, and all this having long stabilities for a photochemical reaction that are more than 100 hours and 200 hours respectively for each one. All this system is being scaled up, and as Celal has explained, will be validated with outdoor sunlight in Turkey, and this needs to be validated for 1 to 5 days continuous work. Okay. The consortium of the project, specifically here, coordination with the University of Michigan in the States and with the University of Peking in China. We are collaborating with them, and the different partners. University of Galway is the one preparing the catalyst for the CO2 and water reduction to syngas. The Peking University working in the Fischer-Tropsch catalyst. The ICIQ together with LEITAT in developing all the photosynthesis system for the solar concentration. Chemtrix developing the flow reactors. The flow reactors that are used in the project. Funditech that is anchoring the catalyst in the inner part of the flow reactor. And then the Michigan University and Burgos University performing all the theoretical calculations for previous to the reactions, and also the life cycle assessment and co-design studies. So CAR, scaling up the system, as Celal said, and Strategy M doing all the dissemination and coordination. That is why we are here today. Very fast, the methodology proposed for the CO2 reduction to CO, a COF-based system within gold nanoparticles and ruthenium oxide that helps in both the reduction of CO2 to CO and water to hydrogen at the same time, okay, in parallel. And for the Fischer-Tropsch reaction, are iron-based with other metals catalysts supported on carbon nanodiamonds or carbon nanotubes in this sense for this syngas, specifically syngas to alcohol obtention. Okay. And all the system is based on solar concentrators to perform all the reaction in flow reaction to increase the conversion during the residence time of the gases inside of the reactor. Okay, all these reactors covered with solar light concentrators and as Celal has shown before, all the system prepared with all these beam splitters and all together. Okay, here you can see the lab scale reactor. It's a very small reactor that works 100, 200 microliters per minute. It's a very, very slow. We have here the. This is the light source. Here is the microreactor that is micro channels and all the systems controlling. This is the. When it's working, it's much more complicated than this. This is the reactor alone with the solar concentrator. Here we have a Fresnel lens for the light, but the solar concentrator is deposited over the reactor. The system working is more complicated. And we also do all the analysis in continuous. So we are working in flow. We have prepared this GZ that can work at very, very, very low flows and do continuous analysis of the reactions. Okay. And at the end, as we said, we have also prepared the membrane separation and purification for continuous separation, both of the oxygen in the first reaction, that it's an inorganic based membrane, and in the second case is by evaporation or with an organophilic membrane to separate the ethanol, propanol, and butanol, that are the three alcohols we obtain more from the water at very low concentration. That it is usually the separation when the concentration of alcohol is high, the separation is easier than at the concentrations we are obtaining because the conversion is low. To finalize, only to show the results at a short commentary of the results we have at the moment, because the project is finishing in December. Okay, with the first reaction, we have really good results. We have CO₂ and H₂O obtention demonstrated, and one sun and at a temperature of 100, 120 is photothermal reaction. What we observe is it's curious with gold, because usually gold doesn't reduce directly the CO₂ to methane, but in this system, what we observe is that at temperatures higher than 200 and at 150, what we obtain is mostly methane. It's an over-reduction, and we obtain directly the methane. We don't know if it's because of the ruthenium, that maybe with the hydrogen is reduced and can reduce the perform the Fischer-Tropsch reaction, because ruthenium is a typical catalyst for Fischer-Tropsch, but it's curious. For the second one, the manganese lithium iron catalyst over nanodiamonds or carbon nanotubes, both catalyzes the reaction, but the problem we have is that if we want the high selectivity towards alcohols, the conversion needs to be very low. If we go to higher conversions, we obtain the standard Fischer-Tropsch products that are methane, ethane, propane, all these hydrocarbons. Okay? And both purification systems are working very well. We can separate hydrogen from syngas, producing the phase reaction with no problem, and also the selectivity of the ethanol purification from the final system is over 80%. Okay, and now at the moment we are scaling up all the system in the SOCAR installation. So let's see in December what we obtain. Thank you very much.
Thank you very much, David.